Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome back to this course on circular economy for sustainable buildings. And today we will continue with design for adaptability, but we will look at some of the benefits of design for adaptability and the larger picture of where this adaptability falls into the circular economy principles and as well as in the sustainable environment domain. So, today we will see design for adaptability. Now, if you look at the benefits of design for adaptability, you can see that if we are looking at a circular human centered adaptive reuse of cultural heritage model, it comprises of the ecological paradigm, the human centered paradigm, because after all whatever we design is for human beings, and the other aspects include energy innovations, technological innovations, urban context and urban landscape. And in the ecological paradigm, the circular human centered adaptive reuse must consider ecology, nature ecosystems and biodiversity. It should consider the ecological economics and the ecological paradigm at large, the economic impact of going for adaptive reuse, and does it fall in the conventional economic approach or do you need to have some innovation in that, and then the circular economy, which is very important, and evolutionary economics. All of this is the ecological paradigm which is directly related to circular human centered adaptive reuse of buildings which have specific cultural heritage. If we look at the human centered paradigm, we need to look at human development, human paradigm, the well-being of human beings which include health and quality of life, the social impact of retaining these buildings of heritage value or otherwise, reducing inequalities leading to equity, the cultural impacts and the inclusion of marginalized people. So, these are all the social or human centered paradigm, whereas here it is ecological as well as economical aspects. So, all of these must be considered when we are looking at adaptive reuse of cultural heritage. Of course, how we use or exploit or otherwise energy, the technological innovations, the urban context and urban landscape, all of this will play, and then we can look at a sustainability or circular model. When all of this adds up, we get a circular city with urban symbiosis, and then we can look at conservation, development, transformation in this holistic manner. Let us look at splitting these part by part and what it means. So, what are the environmental benefits of circular economy or environmental benefits of design for adaptability? Now, when you design for adaptability, you do not demolish, you avoid the demolition aspect, because of which you can avoid landfilling. Look at the amount of garbage that can be accumulated because of landfilling, and when you start dumping on landfills, most of these are either open lung spaces of the city on which you dump all the waste. Therefore, the city will lose its lung space and it will lose its greenery. Also, these are all spaces for recharge of aquifers. And when you start dumping the waste, you end up polluting land which is precious, because your aquifer recharge areas of the city gets reduced dramatically. And when this happens, the rainwater that falls on this garbage or on this waste gets soaked with the pollutants of the waste, and that is what enters into our aquifer, and that also leads to pollution of water, underground water, or even when the water flows like a storm water into lakes, ponds, our sources of water can get polluted. Also, what is the environmental benefit of adaptive reuse? If we are able to avoid demolition and landfilling, we can avoid the use of new material. So, avoiding use of new material. When you avoid use of new material, what happens? You save on virgin materials. So, the process of extraction, manufacturing, transport of new materials also gets nullified, and therefore the entire chunk of embodied energy can be saved. So, it also keeps in place all the natural resources that would have otherwise been withdrawn to produce and also install new materials, and also the pollution or environmental releases that happens to water, air and land because of extraction, manufacturing, transportation, construction, installation of those materials gets reduced, or it just does not happen. Hence, pollution can be avoided on a large scale, and also global warming associated with the creation of new materials and building can be reduced. So, environmental benefits of adaptive reuse are many, and they include: we will not be polluting the land with landfills, we will avoid extraction of new material and virgin sources, and in this process we try to reduce the GHG emissions and hence the global warming associated with the creation of new materials. What are the resilience benefits? So, the use of very ordinary, simple, low maintenance materials which we can get easily, this also helps the building to stand up to the forces of nature. And as you know, with climate change, the forces of nature are becoming really strong. And therefore, what we can do is, we can make the systems much easier to repair and replace, which is also a huge benefit in case there is damage of elements. So, in order to be resilient, first you need to define what is resilience. So, what we can look at is, resilience is use of locally available and robust materials. So, when you start building with locally available and robust materials, you need not really have the fear of complete or permanent damage which is not rectifiable, because the materials required to again reshape the building in the case of any disaster is easy, because you can have the material available easily, and also ensure that you use very strong material, robust material. So, having a very strong structural system can provide greater resilience. So, first is we can get resilience through use of locally available material, having robust material or strong material, and third is having robust or strong structural systems. So, all of these will ensure that we have adequate resilience. Now, let us look at the quality of living benefits or community benefits. Now, what happens is every time you want to demolish a building and then new construction has to come up, it can disrupt the local life for many years because you will start to contribute to noise pollution. There is disruption of sidewalks and streets, and there is dumping of materials either adjacent to the site or no, probably in landfills. So overall, this building adaptation takes less time and causes less disruption than demolition and building new when you start looking at adaptable buildings or trying to go for reuse of buildings. And when buildings are demolished and are not replaced, then that's another bigger headache because you start to end up having vacant plots. Because of that, there is a wastage of resource, and also vacant plots in an urban fabric is never a welcome thing because it can attract criminal activity or it can become a dumping ground and littering place for others. So, when buildings have some architectural significance for the neighborhood design for adaptability, this helps us to preserve the cultural value, and this can contribute to a very vibrant, healthy community and also protect the historic heritage for all. Next, let us look at the economic benefits. Now, adaptable buildings have a lot of inherent financial value because they can be economically adapted and renovated as the occupant needs the changes. Here, what happens is the entire cost and the effort for demolition can be avoided. Now, the cost of rebuilding a new architecture there or a new building there can be completely avoided. Also, if you can put the building to use either for its original purpose or a new purpose, you can generate income for self-maintenance. So, as I always say, there is nothing called waste. Waste is actually a misplaced resource. And see, there is an example in the US where you had a dumping yard like this, where a lot of dry waste was dumped. This does not contain organic waste, it's all dry waste like leather, paper, cardboard, metal scraps, and so on. What they have tried to do is they have tried to bundle this up and make it as blocks. Now, these blocks can be used for various non-habitable purposes and also in places where you don't end up soaking them in water, as they could end up polluting the aquifers. So, it could be something like a robust wall for prevention of something. So, you just stack this up instead of a concrete wall, you just stack it up against a particular place which can separate one disastrous place from another, and so on. So, the uses is something that will depend on what is the waste, what is the size of the waste, what is the context, all that. But all I am saying is the entire process of what you would otherwise do gets resolved when you start looking at alternative options. What could be the approaches for designing for adaptability? How will we design for adaptability? So, the key principles for designing for adaptability will include that we should have large span structures for ease of putting it to multiple use. So, if you have no structures which are say 3-meter wide, the entire grid is only 3-meter wide, the options of putting this place into another use becomes less, because the room sizes will be so small, you cannot have or imagine any other activity for which you need actually larger spans. So, you should start looking at designing for long span structures. Also, start designing for large heights which can have potential for varied uses. So, instead of a routine regular height, start looking at larger heights, so that when you don't want that space to be utilized for what it is built, it can get translated into multiple uses in the same space. Try to design with flat roofs which can have provision for building vertical, so you will be able to go vertical. Have a structural grid and also make use of modular adaptation easily. So, don't go for no random customized grid, but go for a structural grid in which you can have additions done or subtractions done. So, because it's a grid, it is easier for anyone to configure a dimension or a module which can be increased sequentially either horizontally or vertically, or you can even reduce the grid horizontally or vertically. Have very strong structural systems with provision for horizontal and vertical expansion. Besides, start segregating the services. So, don't mix too many services in the same pipe. Don't put electrical and plumbing services. Have separate cores or separate pipes or ducts for each of these services, so that at a later date it becomes easy for you to understand which wiring or which plumbing pipe is going in which direction, what you should tamper, what you should not tamper, where you should break or where you should not break. Because I'll give you a small example. If you look at renovation of a bathroom, now you will have lots of pipes going which is embedded inside the wall. Now you should have separate and clear identity of where those pipes are embedded in the wall. Because what happens is, over a period of time, if you start to renovate the bathroom or something like that, and then there is a small leakage in the existing pipe because of wear and tear, without you knowing, slowly there is moisture seepage inside the wall because of the very small leak. It may be just tiny drops of water seeping out, but over a period of time the moisture in the wall will get built up, and moisture is the biggest enemy of any building. But if you know where that pipe is going, then you can clearly close the pipe at both ends and stop hammering that place for any renovation. If you want to change the tile or anything like that, you will stop putting pressure or tension in that area, so that you can prevent the damage to the pipes. Then use strong and durable materials which will last longer. So, if I take the bathroom example, don't use GI pipes inside. If you use iron pipes, over a period of time, it could be subjected to rusting. Especially if you are not going to have soft water all the time in that building, over a period of time it will rust, get corroded, start having small holes and leakages from it. So, use appropriate materials in appropriate places, and also use very strong and durable materials. Use mechanical fasteners and don't use adhesives. So, if you start pasting elements, then it is difficult to detach them without any damage. So, you can detach, but there will be damage. and then the whole purpose of design for adaptability, resource conservation, building material conservation will go a waste. But if you start using mechanical fasteners like screws or bolts and nuts, it is easy to first see where the joint is, because you can clearly see the nuts and the bolts, and it is also easy to dismember that joint easily without much damage. Also, when you design for adaptability, always give provision for a flexible design. Now, for example, when we talk of joints and adhesives, here I have taken an example where you see it is so easy to identify which member should be no, tampered with in order to remove the elements individually. Now, if this instead of these nuts and bolts, if they would have used adhesive, you wouldn't know at what point the adhesive is there, how to detach the adhesive, what is the nature of adhesive, do you have a solvent for that adhesive, or you will have to end up cutting off that particular piece. You would know nothing of this. So, it is best to use joints which are visible and which we can detach easily. So, here is an example I have taken where if you want to design for adaptability, you can also look at designing it in reverse. What I mean by designing in reverse is that instead of starting and designing a building of how it should be built, you can conceptualize how the building will be detached. So, you should start looking at designing the parts, and also at the same time, I am reiterating that, how the building will look when all the detached parts which are in your mind that come together to form a holistic building. So, when you start giving designs, the design is not only for building a particular architecture, but you should also give design for dismantling that architecture. Then we will have 100% successful design for adaptability. Now, another example which I had already shown you was the cave Kurion by Kengokuma. If you see this building, this looks more like a Lego block. All you can do is you can detach this building easily, because all joints are seen clearly, visibly, and it is more a mass supporting mass kind of a system, because of which the building is standing, and it is not more like the building is held together by major jointing system. It is not like that, and therefore this building is easy to dismantle. Another example that I would like to give is the pop-up house by Multipod Studio, where if you want to consciously dismantle this house, all you need is a screwdriver. The entire house is made up of units, modular or otherwise, which are held together by a number of screws. So, to build the house, you needed the modules and the screws, and to dismantle it, you need just screwdrivers. So, these are all great examples of design for adaptability or design for deconstruction and dismantling. Once you have these materials dismantled, then what will you do? How will you go about it? For that, there is a concept called reuse of building materials through the material banks. So, here you consider the building material in a particular building to be kept like a material in a bank, like how we keep cash in bank. So, the physical place of holding the cash is a bank, and here in this case of architecture, the physical place of storing that material is the building. So, there is something called BAMB, buildings as material banks, a very important concept in the context of circular economy and adaptable buildings. So, instead of looking at materials as used up and then you don't want, you dismantle and throw it away, you actually integrate it into building and then look at it as a temporary storage space. That is the concept behind material banking, and this is actually an offshoot of the circular economy. So, a circular economy model will always encourage materials that are perpetually reusable or recyclable. So, it is never a one-way track to the landfill. Today it is used in this building, tomorrow it will be used in this building, then it could be transferred to this building, then it could go to this building. So, the material keeps jumping to one structure to another but does not go to the landfill until there is absolutely no other choice. And even at that stage, there is a reuse to the so-called waste in some other form, such as recovery. Okay. Now, let's see what is reuse of building materials. So, we have to treat a building as a material bank. So, with materials retaining all their value while they are temporarily in use. So, it needs to be deconstructible. So, you start designing buildings to be deconstructible. Ideally, how to disassemble all the parts and put them back together so that you can reuse in different buildings should also be very clear. So, for that you should start looking at buildings in which you can have modular components as well as materials which can be deconstructed. So, here we look at the example of the testing BAMB result through prototyping and pilot projects, which is done to understand whether BAMB will work. So, instead of stacking materials into a particular building and then looking at it as something which will go to a landfill, there has been lot of experiments and projects through use of dismantleable joints and then use of large structural frames and then understanding how these buildings can be reused in the future. So, the project BAMB, which is Buildings as Material Bank, is a network of 15 partners from 7 European countries who work together to understand and realize the goal of circular economy for buildings. This group is actually developing the idea of materials passport, in which data about the products and the materials that can be used to track their attributes and also give instructions to future designers on how to dismantle or deconstruct the building and also how to reinstall the component which is deconstructed from the building. This data could be incorporated into the BIM model or building information model, or it can be encoded directly on the product so that you don't have to search for this information and this information is readily available. So, ideas like this can someday help us to create a more mature market for reused materials, making it more likely that buildings will be commonly designed for deconstruction and will actually be deconstructed rather than demolished once and for all. And by doing this, we can use the reclaimed materials. So, the first role for any architect in designing around reused material is to raise awareness with clients about the embodied impacts of new materials and introduce the possibility of reusing the materials salvaged from other projects, either for their historic value or for their economic benefit, or at least for the sake of environment. So, we need to bring together all the stakeholders in order to make the BAMB model successful, building as material bank model successful. Now, when it comes to use of reclaimed materials, you need to first start finding materials in larger quantities for a project, which could be difficult. So, it is important for you to have a backup plan in case you do not get sufficient materials that you were actually planning to do. It may also be difficult to work around size constraints unless we start bringing the concept of modularity in the complete or overall building industry. And if you plan to reuse structural materials, they may need to be regraded and recertified by a competent authority. Or what you can do is, if the material is supposedly unfit for its original use, then you could find an alternative use for that material. For example, waste concrete and brick can be recycled for road base aggregates. We can have clean dimensional lumber which can be reused as reclaimed lumber. We can have clean dimensional lumber to be recycled as mulch if it does not have the sufficient strength to be reclaimed as a lumber. Flooring which is supposed to be wasted from one building can be reused so that we can reclaim stock for flooring, wall and ceiling panels through recycling. Then items like cabinets or insulation or working fixtures and appliances can be reclaimed again as cabinets or insulation or bats or fixtures and appliances. Solid door can be reused either as a solid door, or we can reuse it for furnitures and upcycling. Things like flagstone can be reused and reclaimed as flagstone, and decking material can be reused as reclaimed decking material, or probably even as a engineered timber. So, either we can use those materials for its original purpose or find a suitable purpose for which the material can be used because of probably lack of strength or lack of robustness of the material with time. Also, despite the challenges, designing the material reuse can be extremely rewarding, primarily as an environmental process, sometimes even for aesthetic reasons, also for cost savings. So, the expertise of that deconstruction specialist as well as reuse specialist is very, very important for a project. So, if you look at an example where the sustainable building design done with reclaimed wood library, this can be done with 3D scanning technology, in which the waste material is collected, and this waste material, which primarily comes from wood material, this undergoes 3D scanning, photogrammetry, laser scanning, and then the method is material library sorting based on various criteria like strength and durability or sizes and so on, and then this can be reclaimed for a wood based design, which is again a digital building aggregation design based on the sizes that were reclaimed and the strength or robustness of what was reclaimed. So, we can now look at design considerations for adaptable building. So, if we look at it comprehensively, adaptable means the capacity for a building to accommodate effectively the evolving demands of its context, thus maximizing its value through life. This comprises of various issues involved, such as it should be easy to assemble. How does something become easy to assemble? It becomes easy to assemble if it is movable from one location to another, and in its location whether it can be inflatable, what is the weight of the component, can we use it as kit of parts, does it have easy connections, can it be collapsible, and what is the scale of the component. We can also look at how adjustable, the ease of adjustability when it comes to plug and play elements. How can the user control it? Can we store it easily? Is it stackable? Does it have non-fixed objects? Because if it has fixed objects which is not dismantlable, the transportation can become a very difficult task. Does it have detachable connections? Does it have operable elements? We should also look at the less risk and greater return perspective, where is it versatile enough for us to be used in a redesign. So, does it have movable walls? Can we use it for a variety of room sizes, or should all the rooms be only one dimension, 4 meter by 4 meter, 6 meter by 6 meter? Or can we have variety of room sizes? What will be the corridor widths even if it is modular? Is it a framed construction? Does it have flexible and identifiable ducts? Is there a facility for storing this material? And does it involve excessive of anything such as excess service points? Also, how does it look at the changes over time? Is it refittable? How will its performance be? Does it have sufficient access points? Does it comply to standard shapes? Are the connections dry such as screws, bolts, nut, or is it wet connections? Does it have a coordinated system when it comes specially to services? Are we able to prototype it? Does it have interchangeable components? Meaning to say, one column, can it be placed even in another location with another set of beams, or should it be only in that particular place, which makes documentation also very important and slightly cumbersome. So, does it have interchangeable components? Does it minimize points of contact? Then, how much is it susceptible to change or convertibility, so that we can have multiple functions for that adaptable building? Does it have a loose fit? Does it have raised floors or fixed to the ground, under which condition it's very difficult to dismantle it? Is it simple and legible? Does the ceiling height change? Can we have multifunctional spaces? And does it have excess service capacity? Can we consider scalable size? Can we consider product platforms? Can we consider local building materials? Are known techniques used in building and dismantling it? Does it have structural redundancy? Can we have it as modular units? Can we get extra spaces? And also, can we have rooms which can either be divided, or can we have rooms which can actually be combined and made larger? So, all these factors along with BAMB will add together for adaptable buildings and also to consider adaptive reuse of buildings in future. So, with this, we will stop today's class and we will continue next class with another topic. Until then, thank you.